Hello, welcome back to our CSCI for 30 operating system. And for today's lecture, we'll move on to a new topic. It's related to process. Okay, so in the beginning, we will talk about what is about like process, and we try to explain the relationship between processes, threads, and then what's the PCB and TCB. Okay, and if you remember when we mentioned about history, and then we talk about like multi-programming, multi-threading. So actually it's a kind of a similar concept. Okay, so when we move on, when we talk about the concept of process, so we need to know it's a fundamental to the structure of the modern computer operating system. So nowadays, it should be this process. And later when we talk about different scheduling, okay, so we're using the process as a unit. Okay, the evolution in the analysis in the problem of the synchronization deadlock. Later we do have an exercise. Talk about like how to doing scheduling in the OS, also being a major intellectual like contribution of the computer science. So here's the idea. And first achievement of process, if you remember, so we try to emphasize one more time, is that fundamental to the structure of OS, right? So every application, so we break down as a process, we mentioned it, and also it also provides fundamental abstraction. If you remember abstraction, so it allows multi-programming to work. Okay, and it simplifies the application programmer. So point of view, so illusion of complete control of machine. So here's the idea. So if you remember, we talk about abstraction and also illusion. So here's the two achievement of included like for the process. And when we talk about process, actually there are two essential elements. So of a process. Okay. First one is called the program code. If you remember in our previous lecture, we look give you a diagram so you'll see. So the program code like safe. So it's a code of block, and also a set of data associated with the code. Okay, sometimes we need to have some variables, okay, data, so all this. And for this add more things, like one is about the dynamic memory structure. So it supports execution of threads, okay, of control in the process. Later, because we will talk about threads, okay. So threads is also based on supporting of like multi-threading, okay. And the function, so we have a core step, and also we do have a dynamic heap. Okay, because when we have multi-thread, because we will maybe letting different processor to handle different different threads, then we need to have a like a state, also dynamic heap to like keep checking, okay, the progress. Also, we have the safe context information. If you remember, also we have the like the context one. Okay, so try to maintain the kernel. Okay, it support the context switching. So this one also belongs to the multi-programming. If you remember, when we talk about multi-programming, we talk about the context information. So when the processor begins to execute the program code, then we will refer this executing entirety as a process. So we need to remember. So when they really start to execute the program code, so it's a process. Okay. And included there's kind of like several things included for the process. So those elements, so once we really started, so the process can be like uniquely like characterized by the number of elements, including the first one, the identifier, the PID process ID. Okay, so it's a unique identifier. We know which ID. If you open your using Windows, then when you check your task manager, sometimes you see different process they're executing right now. So you see some like the process ID, or if you're checking using on a Linux system, so you can list all the process they're running with the they will also show the process ID. They were telling stage. If you remember, we have the execution stage. Okay, so we're telling, and then the priority. The priority included in this moment, you maybe don't know what's the priority doing, but later for scheduling, then it will be one of the criteria help us to like choosing, okay, which process we execute first. So this one you will know. and then of course the PC, okay, and also the memory pointers, also made some like virtual memory register. So this, and of course we talk about the context data, like for the multi-programming, also the IO status information, and then the accounting information. So all these are the elements, okay. And if you remember, we talked about PCB, right? PCB is the process control block, and this one contains all these process elements, so including our identifier, state, priority, the program counter, memory pointer, context, data, and then the IO state information and counting information of this. It is possible to interrupt a running process and later resume the execution. So if execution had not occurred, so remember this part. And also when we create or manage by these like the PCB, they are also managed by the operating system. Also, there's some like key to allow support for the multi process. So here's the idea. So kind of like here's a kind of like simplified of the process control block. So you can see right here. So when we talk about the PCB, it including all these elements. Okay, and when we talk about process, it also like contain more than that, like we have the program data. Okay, so we have more than that. Okay, and then when we go through, so you can answer the question. So if you go here, so we have like, what's the question one, some more elements. So running on process include, okay. So what will be included for running process? Okay, so, and the next one was the next element. So that's the OS that usually not keep track of running process. So check the what we mentioned about in the PCB. Okay, do we have for identifier? Okay, PC, which is content, or like the memory pointer, okay, process, or the remaining time. So which one is not? Just see. So it's pretty obvious right here. And then next, because we talk about the process, and then we talk about the PCB. Okay, and when we move on, we do have the process state. We talk about state and then state transition model. Okay, so what's the state? Because what we talk about that. So what's the concept of the process state? And then we need to understand some common transition of the process undergo. Okay, so we need to know. When we talk about process states, okay, so from the process like point of view, so when we execute the instruction in some sequence, so it dedicated by the PC, okay, the program counter, and then over the time the PC, okay, so also refers to the code in different programs, so it's kind of like different part of like different processes. And also from the process point of view, so if there's some instruction, so it causes it to freeze. Okay, so you remember when I say it freeze for some period of time. There's different type of reason, but you just like remember there's some one of it is like it will also cause the freeze. Okay, and then also the OS will manage the freezing and freezing. Okay, so the cause of the process is identified by the process state. So you know, okay. So if this process is like freezing or like already unfreeze, okay. So you need to know. And during the execution, if you look at the main memory right here, so we maybe have that dispatcher right here. So it's like occupied. And mainly we focus on if we have multiple process A, B, C, and included in the process with different their own PCB, right? So if you remember different PCB, so we will like have a program counter loading and then start to execute. When we call it a process, if you remember, so once the program code started, then it's called a process. And right here, it's giving you some like trace of process. If we could trace it, so start from like 5,000, 1, 2, 3 till like 5,011, okay, or like the process B start from 8,000, okay, and then the process C start from 12,000. Here's the address of it, so it's showing which like at starting address of the program, okay, and when we need to like combine the trace of the process, then right here we're showing, let's say we're showing from the dispatcher program, it will tell you what's the starting address. Let's say if we start from 100, and then keep going. There was the 101 right here. Okay, and then of course we do have right here we execute. If you remember, we have the process A, B, C, 500, 800, and 12,000. Then we can refer to like program, and then with dispatcher, and we do have a timeout. So right now you maybe have no idea like what's the timeout. Later is related to scheduling of the process, and we going to have like right here maybe keep checking, and there's another process B right here in this part. If we have some interrupt or like the IO request, okay, so we'll go to that, and then we'll come back to the process C, okay, process C, and go back to the process A, and then see if sometimes if the process like finished, then we just like start another one. So right here you can see some like share area, so indicate the execution of the dispatcher. Okay, so there's a dispatcher doing first, and then second column right here, and so second, fourth right here. So it's showing the address of the instruction beginning the execute. Okay, so right here, so that's how we like keep track the process. Start with the first one. If you remember stage, okay, so we have the two-stage process model. So the process just like maybe one of two states, either running or not running. So once when enter, maybe the program is not yet, then we'll dispatch it, okay, and then start to running. If it's completed, then we can exit. Okay, if no, maybe we have some reason. Okay, right now we do have like because scheduling somehow we will pause it and go back to return back to non-running stage. Okay, so after we come back from the dispatcher, then if you see from the this one left column, so we have the process A. So when the execute to 5, then we will have a timeout pause and then come back to 6 to 11. Okay, and after we finish, and for the program process B, so we only have like 4 instructions right here, and after finish, it's done. So we not execute it anymore. So we already exit. Okay. And for the process C, okay, after we execute to like 12,005, and then we will return to the non-running stage and dispatch again. Okay, so right here and continues. So once you finish, then the program exists. So just 2. Okay, and when we have multiple, okay, then we will have a color queuing. So here's the queuing diagram. So once we enter, so we put like all the process in the queue, and then we dispatch it, and then we have processor. Let's say once it complete, it will exist. If not yet, we'll pause it and return back, and then waiting in the queue again, and then dispatch again. So this is when we have multiple processes. Okay, that's called the two-stage process model. And for the process creation, so when we say, okay, when a new process like to be added to those current being managed, the OS, okay, builds the data structure. So they are used like to manage the process, and also it allocates, the OS allocates the address space in the memory to the process. Okay. Commonly those like process they span by the existing process. Okay, like this. Either it can like created by the OS, so we can provide a service. So usually it like that's span from the initial process. Also another one is like another one is span by the internet logins. Okay, so this one is more like about the time sharing. If you remember time sharing, it's one of the scheduling. Okay, and how can we terminate the process? So for the process termination, so it means we need to indicate it's like completion. So the program should like include a halt instruction, so or like explicit OS service call for termination. So we have 2 ways: either the program itself or the OS service. We can do it. So for an interactive application, so the action of the user will indicate. So when the process is like complete, so either like they log off, they're quitting an application, then we are able to tell, okay, so we are terminating the process. Okay, so it time stop. Start with the basic like 2-state. Of course, we do have like built for our modern OS system. Actually, that simple 2 states is not really applicable. So we need to have more like better way to cover all different stages. So this one is called a 5. We change 2 to 5 stage. Okay, so this one 5-stage process model in the beginning. So we have the new one, so we try to admit it. So we put into ready stage. Okay, so we put to dispatch and then running. So this one, kind of like running. If we do have some termination already release it, then we can exit it. For the running, we do have timeout. If you remember, we have one situation right here. So maybe we do have a timeout, then we'll put it back to ready stage. Okay. If we have some certain event, let's say waiting for IO, or we have some like interval comes in, so we'll put it into event waiting. Okay. So wait for it, and then we will put it into the block state. Okay. So once the event occurs, is done, and then we will return back to ready. Okay. So this one is the 5-stage. So you see from new to ready, ready to running, running, exit. Okay, if not yet complete, we can return back to ready, or from running to block. Okay, and then after the event occurs, then we can return from the block to ready stage. Okay. So we're here just showing if we still have like processor A, B, C, and then we have the dispatcher right here. So if you remember, and when we are executing, so in running stage, and then for the ready stage, if we are running process A, this is like from T equals to 0, but actually this 0 is not really exactly like when you start your computer. So we just like say assuming in certain of time, and then we start, and then T equals to 0. Okay. So process A in the running stage, and then for the rest of like process B and C, they are just like waiting in the ready stage. So when they're ready, and after process A have a timeout or finish, then we will move on to the process B. Okay, so we're running it, and we will put it return it back. Okay, for ready stage. Okay, so if process B do have some certain event, so we put it like to the block state. Okay, so the block, and then we'll move on to the process C. Okay, and within this one, if you remember, of course, like dispatcher always occur because we need to load in different process. Okay, so A go to dispatcher B, and then dispatcher and load C. Okay, and then go back, and then dispatcher, and then loading process A. So if you load C in top, so you see certain period of time. So we are loading from the running the dispatcher. Okay. And in this time, like compared with the first one, because like we have the ready queue and dispatch and processor, if you remember. And this time, because we have the block stage, right? So if you remember, we have the block stage. This one, we have 2 queues. One queue is the same we using the ready queue for the processor. If they are changing from ready to running and put it back to the queue. But if they do have something like event, okay, we need to waiting for it, then we will return process either timeout right here we go back to the ready queue, and processor, if we do have some event, we need to wait for it, we put it to the block queue. Okay, so this one after the event occurs, then we can return back to the ready queue. So here's the design 2 queues for our 5 state. And if we have multiple the queue, so if we have different events, okay, then we can design for the queue. So for different events, let's say we have event 1, event 2, until like event n queue. So we can add thing here. So every time when the process say, okay, we're waiting for event 1, so we'll put the add it to the this process to the event 1 queue, and waiting for the event 1 occur. So currently just copying. So this one is called a multiple block queue. So compared to a single block queue, and this one is the multiple block queue. Okay. And also we do have the suspended process. Okay. So when we have this like suspended process, we have the wrapping. Okay. This one is the action like kind of involving the moving part of all process from the main memory to disk. So this is swapping it. If you try to create a Linux system, sometimes they will ask you like how much memory space of it you're going to create as the swap memory like this. So actually kind of it. So we try to move it from main memory to disk. because when we try to suspend process, okay, and when then none of the process in the main memory is in the ready state, then the OS will swap one of the block process out onto the disk into the suspend queue. So it's the idea. And here is called the one suspend stage. So based on this one, extended, we add one more called the suspend suspend. Okay. So here's the same new ready running exit, and we do have the block stage, and based on the block stage, if we do have a process need to suspend, so we move it to suspend stage, and if we need to activate again, so we put it back to ready queue. So here's okay. So this one's one suspend stage. If we do have two suspend stages, then you will see right here. Maybe we'll put it right here, adding the suspend. You can see one is like called the block, and then we can put it to the suspend, or like if we need to activate again, then we can put it back to the block stage, or if we waiting for certain like suspend, then we need to waiting for another event occur, then we'll put it to like suspend or like the ready queue. Okay, then this ready also go back to suspend. So right here, based on the top of it, like the design on one suspend stage, and we extend it. So right here we're adding one more. So we can put different stage including like from the ready to suspend and running to suspend. Okay, or like in the block state, of course, like based on the one suspend stage from the block to suspend. So based on this, then we can do it. Even for the new stage, we try to admit it. Also, we can add it to the ready suspend stage right here, and then we can activate using activate function to change it, put it back to the ready queue. So this idea. And there are some like characteristics of a suspend, because we talk about like suspend. So what is the meaning? So first one is the process not immediately available for execution. Then we can put it into suspend. Okay, maybe this process, okay, may not be waiting on an event. So if we are not really waiting for event, also but there's some reason we will put it into suspend process. Also, this process was placed in a suspend stage by an agent, either itself or the parent process or the OS. So you see, like there are like possible way is that itself need to waiting in the suspend stage, okay, or the parent process need to put this process to suspend, or the OS, okay, for a certain reason. So we need to, the purpose, all this purpose is try to preventing its execution. So if we don't want to let it to be executed, then we try to put it to suspend, okay? And because like when we put it, different from the block, because we are waiting for an event occur, but this time we don't want to let it to execute, okay? But if we were waiting, like let's say we do have some another event occur, is ready to execute, then we put it back to ready or somehow. And then the process may not be removed from this stage until the agent explicitly order the removal. Okay. Also, this is another reason, because we are waiting for the agent, okay, to kind of like explicitly orders, like say, oh, we have to remove this process. If not, just like putting to suspend. And right here we have two more reasons, right? So really talking about why we need to doing suspend. First one, scrapping. So if the OS needs to release a sufficient main memory to bring in a process that is ready to execute. So here's one of the reasons. If we need to bring in, then we need to scrap it. If you remember what's the definition of the scrapping, so right here we're moving from main memory to this. Okay, so if we need to bring in, then we need to swap out, swap in. Okay, and also there's some like OS reason. Maybe suspend a background or utility process, or the process that is like suspended, like causing a problem. If you still remember, like we talked about OS kind of like calculating and predicting what's the next stage is safe, then we can execute. If we know if we execute, let's say we don't have enough resources, then we cannot really execute this process, then we maybe need to put it into suspend stage. Okay, so otherwise it will causing a problem, okay? Or the interactive like user request, if the user may wish like to suspend the execution of a program, for certain like purpose debugging. If you remember debugging, we're putting the break or the interconnection of the use of resources. If we need to use certain resources, then we have to like the user need to suspend this execution of program. Okay, we need to do that. Then we put it to the suspend stage, and we are waiting for the event occur. Like some events like for this situation is like the user maybe like doing debugging, that's why stop, or like the in the connection with the using resources. Once I'm finished, then we can put it back. So it depends on the situation of the user request. Okay, another one is the timing. So if the process may execute periodically, okay, so maybe an accounting system and maybe the like monitoring process, okay, need to check. So it may be suspend while like waiting for the next time interval. If you know, sometimes we can set like cron job, right? Then we are only like executing for a certain time interval. Sometimes you say execute every minute, okay, or once per day or once per week, and then you can put all this process to suspend and waiting. Let's say you can setting you reboot your Windows, okay, we read your Windows like every day in the midnight, okay, so you can like put this process in suspend. We waiting for the timer coming. Okay, it's midnight. Okay, so then we will put it to ready state, then we can execute, put it to running, then we can reboot your computer and execute. So your Windows system. Okay, so maybe we put, and then also maybe there's some like parent. We talk about the parent process request. So if the parent process, they may wish to suspend the execution of the this to examine or like modify the suspended process, or we need to coordinate the activities of various disciplines, then it may be possible. So right here so far will be the possible reasons, okay, for the process suspension. If you want to check, then here's like telling what's the basic two-stage model. So define the possible stage of for the process to running. So which two process? Okay, and also in the five-stage process model, what's the first that represent a various state transition. So you need to match it running to block. Can we go from like running to block? So you can compare all these from block to ready and running to ready. Okay, so if it's possible, then you can choose it. And right here, there's an exercise, but later I will put it in another lab so you can tell. But if you're interested, you can work on this part. Okay, for you to study what's the process stage when a certain time. Okay. So you can put it like when we loading it and then they are ready to execute stage. So you can put in here when we're asking, so what's the process of each process at time 11, then you can put it right here. If we finish, then maybe exist. And then for certain reason, we have suspend ready stage and then ready. Okay. And if they're really finished or suspend, you can see. So right here is a the keywords I scrap out. Okay, so we'll scrap out if you remember that reason. Okay, or the time slice expires. So P2 at time 18. Okay, so when this expire, then what's done, then what you're going to do. Okay, so you may based on the works or like what's the P1 terminate, like at 7 what's the terminate. If you remember the keyword like it's finished, then we are finished, right? So all this like you just compare with the keywords, then you can see. Okay, so just like quickly go through the first part, and for the PCB, we will cover part of it, and we will continue in the next lecture. When we talk about PCB, the process control block, and then the data structure, hopefully you're able to like list and describe the purpose of the data structure and also the elements I need by the OS. So in order to support the process abstraction, and then also the process switching. Okay. Right here, if we look at the process and resources, we have like process 1, 2, and 2n, right? So we have multiple, and if you remember, we talk about, we have like some like virtual memory, the sharing. We do have processor, different I/O, okay, and then also we have main memory. And all these are real concept computer resources. Okay, so for all of them, they all need to request or need the resources in different timing. Okay, so it's more important to how to manage it. And if we look at the like bigger picture of the OS control table, including we have the memory, device, files, and process. Okay, right here. So in the process table, including the primary process table. Okay, so later we will talk go through all the different type of tables. And memory, we have memory table, I/O tables, file tables. Okay, and in the primary process table, we will contain the processes, including like from 1 to n, and all these like process, they contain the process image. Okay, so it will tell you all this. So it's kind of like the big control tables. Like here's the design of it. Okay, and try to cover all the memory tables. First, like what it's doing. So it used it to keep track of both a main, that means the real one, okay, the main memory, and also the secondary memory. That means the secondary is a virtual memory. Okay, so we know create a virtual memory from the disk or hard drive. Okay, so the processes are maintained on the second memory. So they may be using some sort of a virtual memory or simple swapping mechanism. Okay, right now you just need to know we do have some swapping mechanism. So it includes the allocation of main memory to the processes and also the allocation of secondary main memory, virtual and swap. Okay, and also we do some have that protection attributes. If we do have some shared memory regions or read-only regions or these, and also the virtual memory address translation maps. Okay, here will be included in the memory table. Here's the reason, because you know we are using part of our secondary storage. That means the hard drive, our disk. Okay, for creating an area of region of virtual memory. Okay, so that's why we need to know, okay, how can we translate and map with those virtual memory? And for the I/O table, more like simple. So because the OS need to manage the I/O devices and then your channels of the computer system, right? So at any given time, so an I/O device may be available or assigned to a particular process. Then this is the I/O table doing. And for the file tables, okay, so there's some information about existing files, their location, current stage, are they being opened or like reading, like writing state, whatever. Okay, so and the information also may be like maintained and used by the file management system. Okay, so all these are which like the case like OS has a little or no knowledge of the files. Okay, or some other operating system. So maybe they have more like details of file management. So managed by OS. So it depends on. So some OS may yes know a little bit or basically know all the details. So it depends. Okay. For the process table, if you remember, we have process table. So it kind of like maintained to manage the process. So it must be some references to memory, I/O files directly or indirectly, all this. And the table themselves also must be accessed by the OS. So therefore, they are kind of like subject to the memory management. So here it's kind of connect. We talk about the memory management later. And the one, if we remember, like for the process, we talk about the process image, right? So the process image, so it will be typically the elements of process image, including the user data. Okay, the data used by the program for execution, user program. Okay, the program code to be executed, if you remember the program code. Also the stack. We have a stack to store the parameters, call, return address for the function, system call, all this. Okay, so it's the we following the last in first out stack. Okay, so if you remember the stack from those, so there's a last in first out, and the heap. So it's dynamically like allocate the location to hold some modifiable data. Okay. Also, we have the PCB. So those data are needed by the OS control the process. So all these, so kind of like if you see the PCB, and this PCB also belongs to the process image, okay, and here's that also the user data. So if you remember, when we talk about process, there are some certain elements, right? So they are all included in this like process image. And we have the process attributes. So it's about the typical information category we need to track, including the process identifications, stage information, we talk about state, and then some control information. So right here is the bigger picture showing what's the process attribute. You don't have to really dive into it, but we do have some like we did mention before. So including the identifier, right? If you remember, we have the identifier of this process, or some identifier of the process, and create this process, parent process, user identifier right here. So when we say the user data, that means the program itself. Okay, so and also there's some like process stage information. So those including the like user visible registers, and this also may refer references by the mean of machine language that the processor they will execute. So we're in the user mode, okay, and also we have some like control and status register. If you see, we have the control information. So imagine like we have the program counters, okay, containing the address of next instructions or condition code. Okay, this is a result of like most recent arithmetic or logical operation. Also the status information like includes the interrupt. So in the enable, disable flags, if you have the execution mode, also the stack pointer, each process has one or more like the last in first out system stack associated with it. Okay, so here will be the state information. And so there's some like control right here, and also the PCB. Okay, so we talk about the control information, and also the control information including the state, priority, scheduling, and also the data structuring. Okay, so if you the structure, if you remember, we have like 5 stage, okay, and priority. So maybe one or more fields to describe scheduling priority. Okay, but in this moment, we are not yet cover the scheduling. Okay, also the scheduling related information. So this one will be depends on the scheduling algorithm used. So you just need to know, or some like event. Okay, identify and of events the process awaiting before it can be like resumed, and also a data structure. This one may be like linked to other process in a queue. So right here. And we do have like cover I never mentioned is that inter-process communication, different flags, also the process privilege. So they can like grant the privilege in terms of the memory they may be accessed, also that the types of instruction. And also we talk about the memory management. So this one include the like pointers to the segment. Later we talk about segmentation, paging, okay, table. So you just need to know. So when we there's another topic related to the memory management. Also the resources ownership and utilization. So it's like telling how can control the process. So may be indicated. Okay, let's say if we need to open the files, a history of utilization of the processor, all this. So all these can be inside the process attribute. Okay, and so far we will stop by right here. So next we'll move on to the process identification for the next lecture. Thank you.